Hi guys, after a long time I'm back with another video. This time I'm going to talk about the importance of partial differential equations in finance. This is quite a key topic for anyone interested in advanced financial models, because in some cases it's difficult to come up with some closed form solutions, and you have to resort to partial differential equations. So this is quite a key topic in finance. All right. So I will try to follow this outline. Firstly, let's talk about PDEs in general and explain its difference from an ODE. Then I'm going to talk about its importance in finance. I mean some motivation. Then I'll try to explain a connection which is quite critical for the understanding. And the connection is between PDEs and conditional expectations. Then I will discuss Kolmogorov backward equation, which is very, very important PDE. And from KBE, which is the Kolmogorov backward equation, it's just one step to Feynman-Kac. And Feynman-Kac is really the result that you are going to use all the time in finance. So this is a key result for the financial models. And finally, there should be one more bullet point here. I will talk about some applications and we will try to construct some PDEs for given problems. All right. So what's the difference between an ODE and a PDE? ODE is a shorthand for an ordinary differential equation. PDE is a shorthand for partial differential equation. ODE describes a deterministic system, while PDE describes a stochastic system. Well, what do we mean by deterministic or stochastic system? Well, deterministic system is a system where you have no randomness, while a stochastic system is a system where you have any sort of random process involved, right? So that's the key difference. And when we consider the following problem, which is actually just a zero coupon bond pricing formula defined as a expectation of some discounting integral, then if R is deterministic function of time, then B will satisfy an ODE, right? So this if R is deterministic, then you have a very, very simple formula for B, where you have no randomness involved, and this formula would be an ODE. On the other hand, where R is stochastic, you can assume any short rate process such as Vasicek or the SIR model, then B would satisfy a PDE. Okay, so you would have to somehow capture by the PDE how B behaves with respect to the random variable R. That's the extra element you have in the PDE compared to the ODE, and this captures the randomness in R. Okay, so I hope you get the main difference here. I'm not going to go into more details. So why are PDEs important in finance? In general, you need it for derivatives pricing. because the problem of pricing derivative is usually defined as some expectation of whatever is here. It might be a payoff, it might be something more than just a payoff, and that's conditional on the current information that you have. Okay, so this is the value of the derivative or the priced asset, and it's equal to some conditional expectation. And the PDE actually captures what this conditional expectation has to satisfy. Okay, so this is specific to finance. I'm talking about the problems in finance. For other kinds of problems it might not be so, but in our case this will be true. Okay, so the PDE in finance will capture what this expectation satisfies. So you can think of the PDE as some sort of alternative representation of the conditional expectation. This means that you reformulate this problem into a problem into a boundary problem, which is basically a PDE. Okay, so it turns out that instead of solving this expectation, when you have an expectation, you are basically calculating some average value. So instead of solving this this expectation, which you would solve using Monte Carlo, you can solve it using a PDE. Okay, so that's why I say we instead of solving the ugly expectation, we can solve it using a lovely PDE. Okay, and one quite important remark: PDEs only appear in the ethos world. You probably heard of ethos process. That's a process where you have some deterministic component and a Wiener process. And if you were not in the ethos world, this means that the processes wouldn't be just ethos processes, but would involve some random jumps, such as Poisson jumps. Then you would not have PDEs, but you would have PIDEs. This extra I means integral. So this would be partial integral differential equation. Okay, so the information that I provide here are only related to PDEs, and PDEs are connected with the ethos processes, right? So bear this in mind, because there are some more complicated problems where you have non-ethos processes, and this will generally lead to PIDEs. Okay, so in order to discuss some more details about the PDEs, we need to talk about the ethos processes and also about ethos lemma. So we in general assume that there exists some d-dimensional ethos process x, defined using this stochastic differential equation, where mi is a d-dimensional vector, sigma is a matrix with dimensions d times p, and this is the differential of standard Wiener process, and it's a p-dimensional column vector. If you then have some function, this must be some deterministic function, some nice function of time t and the d-dimensional ethos process, then its differential can be calculating using multidimensional ethos lemma. So this is the form of the differential that you would have. So you would have to calculate the partial with respect to t. Then you would have to calculate the partial with respect to all the ethos processes in the multidimensional process. Then you would calculate the second order partial with respect to the processes xi, xj that are indexed here. You would take into account the volatility term here. This means transposed, and you would just simply pick ij elements of this result in here in the brackets, and then this would be multiplied by dt. That means this is like a deterministic component, and this last part is basically the stochastic component, okay, because you have this linear processes here. Okay, so this is multidimensional ethos lemma, and tells you what's the differential of some function f that is subject to t and the multidimensional ethos process x. All right, I am telling you this because we will need it later on. So if you are wondering why I have this here, that's here in order to support the slides in the future. All right, so how do we connect PDEs with the conditional expectations? Recall that at the very beginning I told you that there is some nice connection between PDEs and the conditional expectation. Yeah, that's true, and we try to somehow establish this this connection here. So let us assume that we have some function u that is subject to time and the current value of the ethos process. Okay, so this is the current x is the current value of the ethos process, and it's defined as a conditional expectation of some function g whose argument is x at some terminal time t. So if you substitute, and the g is defined like that, that means that it's equal to the terminal state of the function u. So if you substitute this u here, you get that u as of now is equal to u is equal to the expectation of u at some future time, right? So this means in such a case that u is a martingale. And how do we simply define a martingale? Well, martingale is a driftless process. This means that it has the dt component equal to 0, and because u is a function of the ethos process x and time, we can apply ethos lemma to find du. So we basically, instead of df, we are calculating du, okay? And then we will take a look at how does the differential look like. And because we know that u must be a martingale, then we need that the dt component, which is essentially this one, would be equal to 0, okay? So this is basically what we do here. We establish some auxiliary process z, and we basically this is basically the result from the ethos lemma that I explained to you earlier. So you calculate du using the ethos lemma, and to be able to have some shorthand notation, we collect some terms and place it into this variable, and the other stuff that's basically the tail of the ethos lemma, this one with the randomness, we place it here. Okay, so we have something times dt where no winner process is involved, and then we have this winner process here times something else, and it's extra. Okay, we also use this calligraphic A to collect all the terms here. That means all the derivatives that are with respect to the spatial variables and not with respect to t. Okay, so this t derivative is here, and then the rest is collected by this term. Okay, so like I said before, in order to make u to make u martingale, we must have zero drift in du, and that can only happen if this term here is set to 0, okay, because it's the dt term, it's the dt coefficient. So if we take this whole thing and set it equal to 0, we basically get a partial differential equation, because you have the calligraphic A that represents the partials here, and we have a partial differential equation with the terminal condition that we have defined here, and this partial differential equation is called Kolmogorov backward equation. And this Kolmogorov backward equation basically describes the evolution of the future evolution of the conditional expectation, right? So that's a very, very important in finance. You won't use it in the most cases, you won't use it directly, but it's just very close to the applications. Okay, it's very close. You are just one step from the applications when you understand Kolmogorov. And here I have a teaser question. Can this Kolmogorov be used for Black-Scholes? So let's go back, and we know that the Kolmogorov backward equation solves this expectation. But what do we have in Black-Scholes? In Black-Scholes, instead of this G, we have here something like E to a negative RT times and now we have the payoff function, so it could be max K S X K 0. So this would be this would be this would be it would be like this. This would be g of x, but we have some extra discounting term as well here, and that's really not what can be captured by the KBE. It just simply cannot incorporate the discounting term, and that's what makes it difficult for the applications. That's what makes it unsuitable for the applications, because you have the discounting there. You don't only have the payoff. If you only had the payoff there in the expectation, that would make KBE suitable for the pricing itself. But once you have the discounting term there, you can't really use it, because it just simply cannot incorporate the discounting. So can this be used for the Black-Scholes? Well, not in general, but imagine the case when you have risk-free rate equal to 0, then you really have no discounting term in the expectation, and you would be able to use the KBE. Okay, so KBE can only be used in connection with Black-Scholes if you have like 0 risk-free rate. Okay, that's a special case. So we need something else. We know that we are quite close. We can somehow calculate or get the PDE for the general conditional expectation, but we need something slightly more flexible, that can incorporate some extra terms that appear in the conditional expectation. Okay, and this is what the Feynman-Kac theorem will give us. So what's a Feynman-Kac? Feynman-Kac, the result of Feynman-Kac, you can think of it quite loosely as a generalization of the KBE of a KBE. Okay, this means that you won't only take into account this sort of expectation, but you could have something more complicated instead of just G here in the expectation. Okay, so it can handle more complicated expectations, and it allows to find a PDE for these more complicated expectations. And this is really what you need for finance, because many financial problems can be or are defined actually using this sort of complicated conditional expectations. And of course, it's convenient for pricing of derivatives and even other securities. It doesn't only need to be derivative, it could be a risk-free bond, let's say. I will illustrate it on an example. Okay, so here is the main statement of Feynman-Kac. So if you have more complicated expectation of this form, where of course the random process X is Ito's process, and this eta is defined using this, I call it the discounting term. Then this U satisfies this PDE. Okay, so this is the PDE that is populated by Feynman-Kac. Okay, and the great thing about this more general form of this expectation is that really many problems can be formulated this way in finance. It seems to be quite complicated. It's not, and really it's quite flexible, this this general form. I will illustrate it shortly. So how do we use the Feynman-Kac result for Black-Scholes? Well, we can do it together. So let me just simply kill this one, and how is the option price VTT conditional on X defined? Well, that's defined as a conditional expectation of some discounting term times g of x of t, that should be big T, conditional on the current value of the stock. Okay, so this big X, that's the price of the stock. So how do we employ Feynman-Cauchy? Well, we can think of this term here as a special case of this integral. It should be like this. Is equal to, and that's really what corresponds to this expression here, this eta. Okay, so we have a problem where we have this eta times this function g, which is the payoff, and we don't have this integral present here. That means h is set to 0. Okay, so we in the Black-Scholes formula we only have these two terms involved, and in the Black-Scholes case, not in the formula, but in the Black-Scholes case we have only these two terms involved, and we don't have this more complicated integral involved. Okay, so we can disregard this integral. So how does the PDE look like in the Black-Scholes? Well, using this result here that's directly populated by the Feynman-Cauchy, we just simply have, and now we take the partial with respect to t, then we, according to Ito's lemma, take the partials with respect to the spatial variable, which is the stock. So we have x r times x. I like to use small letters in the PDEs. I don't know why, but I just simply like it more. So this really represents the big X. It's just nicer to have small letters in the PDE. So we take the partials with respect to spatial variable. That's the first order partial. Then we take the second order partial where we have a coefficient 1/2 sigma squared x squared, and then we have this second order partial. Okay, so this is basically the calligraphic part. It's captured, and this is the calligraphic A, and basically represents this part, right? Okay, so these are the spatial derivatives, and then, like I said, in our case, h is equal to 0 because we don't have this integral there in the expectation. So h is set to 0, so we have nothing in here, and then we just add negative. Instead of m, we have r here because because we have the e to the negative integral here. So that there we have r, instead of m. I'm just using a general variable here, but in the most cases you will have r here. So we just have negative r times and and then the value of v, because we are not working with u here, but we are working with v, is equal to 0. And yeah, that's really Black-Scholes and Black-Scholes PDE, and we basically constructed the PDE using Feynman catch. Okay, this is how we did it. There are some other ways. Using the hedging arguments, you can get the same result. But the great thing about Feynman catch is that you don't really need to think about the hedging stuff, and you don't need to take that many steps to get the PDE. You just need to have the expectation, and you need to know the processes underlying the exact form of the underlying process X. So in our case, it was dxt. I should have mentioned this before. I kind of forgot. I thought, because I thought you probably know it. But the general form of the dynamics of the stock is this one. Okay, so you can see the presence of the drift term here, and the presence of the volatility term squared in here. Okay, and the r here, this really comes from the this doesn't come from here, but it comes from this part. Okay, so the r at the very end always comes from the discounting part. Okay, so this would be the Black-Scholes PDE. To make it complete, you should really add the terminal condition, where you would simply say that v, whatever it is x, v at the terminal state is equal to j of x. Okay, maybe the x can be here. Okay, so this would be the derivation of the Black-Scholes, and we can take a look at on one more example. This is going to be slightly more complicated, but I didn't only want to go through the well-known case. Let's take a look some alternative. So let's imagine this pricing problem. You are supposed to find a formula for a coupon bond, for a risk-free coupon bond, that is whose short rate is subject to Vašíček model, but the Vašíček model has a volatility which is subject to Cox Ingersoll-Ross model. Okay, so this is a more complicated problem, because you now have two random processes involved, not only one, and you are about to find the PDE for the coupon bond. And we have some extra feature here. We have the coupon bond. We don't only have the zero bond, but we have a coupon bond. So how do we actually approach this problem? Well, first of all, you need to start with forming the expectation. Okay, so you need to formulate this coupon bond pricing in terms of the expectation operator. So well, yeah, let's do it. So I will use again v for the value of the coupon bond, and I know it matures at time big T, and it's subject to actually two random processes, x and v. Okay, this is the sorry, 1b x, it will be the short rate, and the short rate is furthermore subject to some volatility, which will be captured as a square root of variance. So this is the variance, and I will use its square root to define the volatility of R. And it's equal to a conditional expectation where we have something conditional on R of t is equal to R and V of t is equal to simply V. Okay, so how does the expectation for the default-free coupon bond look? How does it look like? Well, imagine that you have a bond that pays 0 coupons. So let's assume that let's assume away the coupons now. In that case, you would just simply have the well-known expression that you saw at the very beginning of this presentation, and that's the expression for the 0 bond. Okay, so this would be the expression for the 0 bond, and now we need to add the coupons, but we also need to discount the coupons. Okay, and I'm not going to go into more details here, but you need to know that there is another integral here. I call it coupon integral, which basically represents the cumulated expected cumulated discounted value of the coupons. Okay, and we assume that there is some coupon rate C, which can be a constant. It might not be a constant, it might even be subject to R, but assume it's a constant, times, so this would give us the cumulation of the coupons, but we need to add the discounting term, so we just simply take this discounting integral and we assume that it's continuously discounted. The coupons that you receive are continuously discounted. Okay, yeah, so this is the formula that would be valid for the coupon bond with 0 default risk. If you had default risk involved, that might be even more complicated. You would have to take into account the probability of default, and this probability of default is usually subject to some other random process. Let's for instance, it might be a default intensity, or in the structural models it might be the value of the assets. So this would really be slightly more complicated, but it would still be manageable in terms of a PDE. Okay, that's important to know. All right, so let's focus on this particular example and let's see how it fits to the Feynman-Catch expectation. So I'll make it smaller. You know, you can see that this is again this eta here. M corresponds to R, and now we have the second integral exactly in the form that we need, because we have this eta here, and that's basically this e2 something. Okay, so this eta here is basically this part, and the h here is the c here. Okay, so we have our problem defined so that it's suitable for the Feynman-Cauchy theorem, and we can apply the Feynman-Cauchy theorem to obtain the PDE for this given valuation problem. Okay, so let's go ahead and do it. First of all, before I do it, I will write out the processes that are involved. So dr, that's the Waschicek's dynamics, will be subject to the following dynamics. Kappa 1 times theta 1 minus r t dt times, and now we have the square root of the variance times dw1 t. So this is the Waschicek's dynamics with volatility, which is defined using the square root of variance, and the variance will be subject to Cox Ingersoll-Ross. Okay, so dv is equal to, so that's the dynamics for the variance kappa 2 times theta. Oh no, I hate this. I never know how to get this back. Yeah, cool. Minus 9 t dt plus sigma 2. I don't really need here the subscript 2, because I don't have any other sigma present in the system, but to make it very clear that it's belonging to the dynamics of the variance, I'm using the subscript 2 as well as the other coefficients here. Okay, times dwt. So that's another linear process, and we assume that these two processes are mutually correlated. Okay, so this is the definition of the random processes involved in the pricing, and now we are looking for a PDE that solves this V. We also have, it should be basically added here, that V at maturity is always 1, because it's a risk-free bond, so it always pays the par at maturity. Okay, that's given, that's the terminal condition. Okay, so the question is, what's the partial differential equation for the value of the coupon bond? So applying the Feynman-Cauchy, we immediately have partial of with respect to t plus, and now we collect all the partials, the first order partials with respect to R and V. So we have this drift term here times derivative of V with respect to the short rate. This comes from the Feynman-Linkages theorem times, and now we take the other one, and I just do it using copy paste because it's faster with respect to V plus. Now we process the second order partials. So we have 1/2 times this term squared, which means just V, times the second order partial V with respect to R plus, again copy paste. Here we have this term squared with respect to V. Then we have an extra term because we have to take into account the correlation of the Wiener processes. So we have to, so that the mixed derivative appears, and the mixed derivative will be equal to, or the coefficient of the mixed derivative will be equal to the correlation times the diffusion components. It again comes from the infinitesimal generator here. So if you rewrite it this, if you got into details of this, you would get the mixed derivative as well. Okay. And then we again have the second order partial with respect to R and V. And now what do we have there? So we have this corresponds to the calligraphic A times V. And now we have something extra there. We have this H, and I told you H is C in my case. Okay, so because it's next to the discounting integral, which is eta here, so we just simply use the, instead of H, the value of C, and then we have M, negative M, and M is in our case the value of the short rate, so that's R minus R times V is equal to 0. Okay, again with the terminal condition, and I can just copy paste it, which is this one. Okay, so this is a two-dimensional partial differential equation that describes the price of the risk-free coupon bond that pays coupon C continuously in time, and you are given the following dynamics of the processes. You have the process for Vasicek model that really drives the short rate, but the volatility in the Vasicek model is subject to another stochastic process, which is which is Cox, Ingersoll, Ross, and this has the following dynamics. And we furthermore assume that the linear processes are correlated with some coefficient rho. Okay, so this would be, you can see it's quite a complicated PDE because it's two-dimensional. It's more demanding also in terms of the numerical solutions, but it can still be solved. It's quite okay if you know how to do it. And I believe that's pretty much enough for you to understand the subject. All right, and finally, all right, so this would be to the explanations of the of how to find the PDE for various pricing problems. And now finally I would like to provide you with some discussion about the partial differential equations. Well, this could be also a slide, at the very beginning of the presentation, but I believe it's quite a nice conclusion for you to see it at the very end, because it will turn out that you only deal with some specific problem or some specific PDE in the finance, okay? And I will show you why. So the general PDE can be written in this form. This means that this is a shorthand for second order partial with respect to variable t. This is second order partial with respect to t and x, etc. You get the idea. This is the first order partial. And if you rewrite a PDE in this form, you can calculate some discriminant. Okay, so the discriminant is driven by these three, is driven by the coefficients of these three terms, so of the second order partials. Okay, and this discriminant determines what kind of PDE you are dealing with. So if the discriminant is negative, then your PDE would be elliptic. An example of elliptic equation might be the Laplace equation, and you can see you have it's generally written in, it has this form. I don't think it needs some more explanation. But the key thing is that it has second order partials here. Then if the discriminant is 0, then you are dealing with parabolic PDEs. An example might be the heat equation, where you have partial with respect to t and partial with respect to second order partial with respect to the spatial variables. Okay, and the third case is when you have positive discriminant, then you have hyperbolic PDE. So this would be an example of the wave equation which is written here. And the key thing in finance is that you will always be dealing with this parabolic PDE. Okay, and why is that so? Well, if you take, you can basically drop this part of the PDE because it plays no role in the discriminant. But if you focus on these coefficients here, then you know that the Feynman-Kac theorem never gives you something with respect to, never gives you a term where you would have derivative, like second order derivative with respect to time. It's never there. You also never get this term. So you never get this term because you never get from the Feynman-Kac the second order partial with respect to time and the spatial variable. All right, and this is so if A and B are always 0 by definition of the Feynman-Cauchy theorem, then this discriminant will always be 0, and this guarantees that you are always dealing with parabolic partial differential equations. Okay, so in other scientific areas you might get this Laplace equation or wave equation, but in finance you'll always get this parabolic equation. So that should really motivate you to learn something about the parabolic equations, and you can assume away the whole machinery that's related to the elliptic or hyperbolic equations. Okay, because if you are then going to solve the PDEs numerically, you need some numerical schemes for PDEs, and you basically now know that you only need numerical schemes for parabolic partial differential equations. Okay, so that's the key takeaway of this slide. Just focus on the parabolic PDEs, because these are the most I would say commonly used equations in finance. Okay, so thank you for your attention, and I hope that the next time I will prepare something. I hope to prepare something for the numerical solutions to the PDEs. Okay, thank you.